There is Justin David, and he'll be talking about higher spin entanglement entropy in CFT and holography.
Yes, yeah. So yeah, okay. Let me see. So of course, as we have seen from the previous talks and previous, this is on, right? Yeah. So as we have seen from the previous talks and also from the other talks, this entanglement entropy has been is a sort of important observable in quantum field theory, and our perspective, as just as Rob's talk earlier, is to understand it in the holographic context. So let me again go through the definitions which were run at least 2 times yesterday and today, and again go through it. So first, let's go through the definition. So this is based on, okay, I should say, it's based on some work earlier this year with Shavik Datta, who's my student at ISC, Prem Kumar and Michael Ferrellino. Prem is at Swansea, and this is a student at Swansea, and also a work which is going to appear soon. Let's go through the definition. So definition again is a Hilbert space. Consider the Hilbert space, partition it into 2, A and B. So for our purpose, it's good to just instead of all those surfaces which were drawn before, just think of a real line, because we will be mostly in the 1+1 context. There is an interval of length delta. This is our region A, and the rest is the region B, and we are tracing over degrees of freedom of B. So we construct the reduced density matrix rho A. So suppose we have the density matrix of the full system, construct the following. Okay. Trace over the B Hilbert space. So we construct the rho A, and of course the entanglement entropy is defined by the von Neumann entropy. Okay. And one of the things you can see is that if rho was, I mean, it's good to keep in mind, if rho was a thermal state, if rho corresponds to the density matrix of the thermal state, and if the size of the system was complete, was full of the full system, it should be the thermal entropy. It's good to keep this in mind later. So this is the thing. So and as we saw in the previous talk, there is a closely associated concept, the Rene entropy. So let me just write it here, which was defined. So SAN 1 by 1 minus n log of trace rho A to the n. And as you can see, if you do a Taylor series expansion in n, I mean, of course, this is integer, but suppose we analytically continue, this is 1 plus trace of n minus 1 rho A log rho A plus dot dot dot, and you get the von Neumann entropy. So SA limit n going to 1 is the entanglement entropy of region A. So of course, as we have seen in quantum field theories, these are difficult. It's quite difficult to compute this quantity, as it was mentioned in the previous talk. But in 1+1 critical systems, so 1+1 dimensional conformal field theories, there are quite a few exact results, and it was also stated before. So suppose we are in this context, line with the region delta. So this is a spatial line with the region delta of length delta. So SA was C by 3 log delta by. Let me just quote the results first. I will actually give a small derivation of this so that people realize this, how it comes about, because it will be useful for later. So this is some UV cutoff. Similarly, if this was put on a ring, so we can relate it to by a conformal transformation, but if this was put on a ring, if the spatial circle was on a ring, and this was the size delta, so then SA is C by 3 log L by some cutoff 2 pi epsilon. L is the size of the full region, L is the circumference, say, it's sine. So the periodicity comes about. So the periodicity, C is the central charge. Okay, single interval we are talking about. And if the CFT is on an infinite line, but at finite temperature, beta, So, it is on a cylinder. Okay. So, this is a spatial, and but this is temperature beta. There is a similar formula. You can actually again conformally map things and get these formulas: C by 3 log beta by 2 pi epsilon sine hyperbolic pi delta. So, imaginary periodicity. So, these are the known sort of formulas. So, as you can see from this expression for a single interval, entanglement entropy does not have more information for a single interval and in 1+1 critical systems. It does not have more information than, say, the Boltzmann formula or the Boltzmann-Cardy formula. So, in 1+1 CFT, the only information of the CFT is the central charge, which is similar to what you will get for instance, if you compute entropy per unit length of the CFT, and there is this famous formula pi squared by 3 at high temperatures. So, this information is already in this observable. A single interval has some information, but not so much as you would like, and in some sense it is universal. And that is one of the ways, I mean it was the reason one could use this results to check the holographic formula of Ryu-Takanagi. And let me go through that formula again in 2+1 case, so that people are familiar with it. So, yes. Yes.
It's kind of a trivial thing, but I've always been confused.
Yes.
A special case of this CFT would be a
free CFT
massless
field, yes.
But then there's a zero mode.
Yes.
Is that being left out of this calculation?
No, I think that is also part of the calculation.
But it won't be regulated by an algebra cutoff. You need some other kind of thing, a small mass regulator or something.
Yeah, perhaps. So, maybe when I go through the calculation, so these calculations are done using the replica trick and using the insertions of the twist operator. So, that is how the calculations are done. So maybe when I go through it, okay, actually I am going to go through this calculation again, so we can discuss that again, and it can be done in free. Okay, I will, when I come to it, we will discuss that. Okay. So let me, I will come to it soon. So the holographic derivation or the holographic proposal of Ryu-Takanagi. Okay. So look at, so again, so this is a conformal field theory in 2+1 dimension, and therefore the bulk is some ADS3 space. It has the right isometry, okay, and this is the ADS3 metric. So let me just go through it. So some things becomes explicit here, and so cosine hyperbolic squared rho dt squared plus d rho squared plus sine hyperbolic squared rho. So this is the ADS3 metric in spherical coordinates, and what you are instructed to do is look at the time slice, constant time slice. So you are looking, so the circumference is of length L, and you have a region delta. And you have to look at sort of the minimal surface or the geodesic, which starts at the point A or the two endpoints of the length. So I have been calling the region as A. So 2 endpoints, you are instructed to compute the length of the geodesic. So if you throw away this is basically a hyperboloid. So it's a hyperboloid, and it's quite easy to compute geodesics on a hyperboloid, and then you are interested to, I mean, evaluate the geodesic length. So you're instructed to compute geodesic length by 4g Newton in 3 dimensions. So let me give you the formula for the geodesic length, so that it is a little bit, if people remember the geodesic length for a sphere, this is quite easy to see. Geodesic length of the geodesic by r is equal to 1 plus 2 sine hyperbolic squared rho naught sine squared pi delta by L. So this is the formula, and delta is of course the points, and L is the full circumference, okay, and rho naught is the radial point at which this geodesic starts and ends here. Okay, rho naught is the radial direction. So that's the radial direction. So you push out. As was talked about in the last talk, so you have to look at a cutoff where rho naught is very close to the boundary. So you push rho naught close to the boundary. So you can exponentiate all this. You can exponentiate this, and if you do that, you get length geodesic by r is equal to 2 log e to the power of rho naught, because you can exponentiate. The 2 comes because of the squared sine pi delta by L. Okay. So then if you calculate area by 4 g Newton, it's 1 by 4. So g Newton has another, you can use the Braun-Henner formula for g Newton, 2 central charge by 3 r, r is the radius of ADS, times r times the length of the, so this length of the geodesic, r times 2 length e to the rho naught sine pi delta by, so you substitute this inside here and you get c by 3. So the r cancels, you get c by 3 log e to the rho naught sine pi delta by L. And e to the rho naught was the UV, it played the role of the UV cutoff, the radial distance. So this is a sort of a, I mean, it's easy to do in 2 plus 1, it's explicit, it's quite simple to do. So let's go back to the CFT again. So as I said, I will derive this. So let's go back to the CFT again and see. So as I said, first, it doesn't seem to have more information other than the central charge. So that's the first. So how can you get more information? So let me just talk about that first. So one gets more info about the CFT from this observable. So one is method 1. Let me do method 1. Consider more intervals. So it was mentioned briefly before. Consider more intervals. So if you consider more intervals, so basically the relevant quantity is actually, if you and this was your region A. The region A is the union of this interval and this interval, and the relevant quantity actually is a function. The entanglement entropy is a function of the cross ratio. So let me just write f of cross ratio. So it's a function of the cross ratio actually, say let's call it x. Okay. And as you expand this quantity in powers of x, this entanglement entropy of this formula, you get information about the spectrum of the theory. So that's the sort of how to get more information. This is one of the methods. Let's go to the second method. All have been studied detailedly, and also they have been examined in the holographic context by various authors. So let me mention about method 2. So method 2. Okay. So put the system on a finite circle and finite temperature. So that was not covered with all the cases, finite temperature. Okay, that was not all covered by all the cases I mentioned. So, what is it? So there is a region delta, there is a circle of size say L or R, and then there is also temperature beta. So the system is actually on the torus. So then the entanglement entropy has, of course, the leading formula, which is like the cylinder, plus corrections, finite size corrections. So the systematic set of finite size corrections. And in fact, for free fermion theories, it has been, Taganaki itself initially evaluated this, and we have recently evaluated it for the free boson theory. And you can use that to check against, because one of the things is that the Ryu-Takanagi formula does not capture finite size corrections, and evaluating it for such certain classes of theories gives information about the finite size corrections. And in fact, the leading ones we can actually extract out of gravity, and there has been a lot of developments, trying to understand how to get finite size corrections in gravity as well as.
But I have a question back on this.
Yeah.
What happened to those terms that came from the single interval? Are they not there anymore?
Oh, that's also there. That's also there. So I'm saying in addition to that.
In addition to
Yeah, you get these functions of cross ratios. Yeah.
that the cutoff doesn't enter into this.
Yeah, in this one the cutoff doesn't enter. Yes, that's right. Yeah.
So it's an actual finite correction.
Yeah, it's a finite quantity. Yeah, it's a mutual information characterizes this thing. Actually, there's something called a mutual information. Yeah, between the two. Yeah, and that is finite. That is independent of cutoff and so on. Yeah. Yeah. Yeah, the initial ones, I mean, the first term would be like the lowest lying conformal primary and so on. But as you expand in X, subleading powers of X, that has more information of the spectrum. So there has been some work regarding this, calculating finite size corrections both in the CFT as well as in the bulk. But what we will do is we will consider another direction to explore here, method 3. Okay. So it looks esoteric first, but I will try to motivate it. Consider CFTs deformed by holomorphic currents at, say, temperature beta. So the temperature CFT is at temperature beta, say beta. Yes. Yeah, they depend just on the, see, this is what is this? This is L times temperature. So it just depends on the size of the torus. So these are the quantities. It's like, it's basically the Q expansions of the torus. Yes, yeah, there are these methods, only 2 plus 1. 2 plus 1 is where the development methods are very sophisticated, because as this Lukovic-Maldacen has think, those proposals can be carried very precisely. You can construct the bulk geometry very precisely using this many handle body geometries. You can construct it extremely precisely, and there are techniques to evaluate the gravitational action of those geometries actually. I think Faulkner and Hartnell and all were involved in developing that. Okay, so but what we will do here is basically consider method 3, where we are considering CFTs deformed by holomorphic currents. In fact, we will discuss spin 3 current, but we have also done spin 1, spin the stress tensor and so on. And the temperature is at, the CFT's temperature is held at beta. So let me just give the sort of, to make it concrete. So we have SCFT plus mu d squared WZ plus d squared Z bar WZ bar. So this is some 3-0 current, say 0-3 current. You can do 1-0 current or 2-0 current. And what we wish to do is basically find the entanglement entropy, okay, of a single interval and SA. So of course you will have the cylinder answer, because this is a system at finite temperature. You will have the cylinder answer, plus you will have corrections. So this is scaling. This is just by scaling, and some function of beta delta. Yeah, sorry. Yeah. So yeah, we can do that. We have both. The analysis is holomorphic current, so it's actually a sum of the terms. So mu squared beta squared and this object. Okay. So this is by scaling. You get this by scaling, and then there is this function. Okay. And we are interested, of course, in computing this function. And what we will show is that this is universal. I will define that soon. It is universal for any theory which admits a W3 current. And because of that, because the fact that it's universal, we can actually compare this correction to the holographic proposals. So there are holographic proposals for theories with higher spin currents. Actually, the proposal was given by De Boer and Jotard, and so we can compare it. So let me again go back. So outside, I think maybe string theory or very specific classes of string theory people, you might think this is some like okay, some quite esoteric thing to do. So let me just motivate it, put this in a little bit more context first. No, no, we didn't. We actually we did very mundane things. We did free field theories, free boson, free fermion. We did the computation. We saw they were same. Then we checked the holographic proposals of de Boer and all. They were the same. And then we had a general method after that. So I will, if I have time, of course, I will tell the general method. So yeah.
This is on a circle, and there's an interval of
Length delta, yeah. And that, and it's at finite temperature, yeah. It's at finite temperature also. This finite temperature. Oh, this, yeah. The CFT is on line, on a line. There's a delta, and the circle is the temperature, and there is a chemical potential mu. It can be various spin currents, but in particular we are interested in spin 3 actually, but we have results for spin others also. But yeah, so this is the configuration. So we have a CFT, delta and p. Okay, so yes. Yeah, I understand, but I mean, I'm talking about talking to a general audience here. I mean, I don't know whether there are condensed matter theorists now; they've all disappeared. So, yeah, I understand. Yeah, free theories have, but you know, I'm just maybe they've all disappeared, so it doesn't matter. So this one. Why is it of interest? What is the motivation for this? What's our motivation? So basically, CFTs with higher spin symmetry is of interest because of one of the reasons. Reason it's of interest is of the proposal of Gopakumar and Gebediel. Okay. So basically, they had a minimal model CFT with actually a W infinity. That means a whole infinite worth of these higher spin currents at coupling lambda. Okay. There is some parameter in the W infinity algebra which has this parameter lambda, and they proposed a dual to be a Vasiliev theory in ADS3 with an with infinite tower of spins. And this is basically a Chern-Simons, just because it's in 3 dimensions, it's a Chern-Simons theory based on Hs lambda. Okay. And in fact, if you take just the entropy of a CFT with this symmetry and deform it exactly like this, entropy. Now, let's not talk about entanglement. The entropy, there were calculations again motivated by holography for the entropy, thermal entropy of CFTs. So this is the Cardy formula, okay, the first formula, and then there are corrections. Okay, and mu to the 4th, these are the chemical. So I'm talking about thermal entropy. So from this term onwards, there are of course this lambda dependence, the parameter of the W infinity algebra, but this term is universal. There is no lambda dependence of this W infinity algebra. There is systematic correction. I think till mu to the 6th. I think Gebediel and his collaborators have gone to the mu to the 6th. And of course, what is nice about this is that there are black holes in this theory. I mean, at least thermal states, so to speak, in this theory, where you can compute it exactly. So there is a closed form formula for the thermal entropy of a black hole like state, in this theory, closed form formula in mu, beta and lambda, and it has been, of course, it's a closed form formula, and you can expand it in orders of mu. You can keep expanding it in orders of mu, and of course, it agrees with the CFT calculation. Okay. It is agrees, of course, the CFT calculation has been done till mu to the 6th, and it agrees till that form. So this is, f of lambda, there is some, every order there is an f of lambda which is known. And it agrees, of course, with the this. Yes. Yeah.
So this mu is dimensionful.
Mu is dimensionful. That's why it's mu squared by beta squared.
So is it a CFT?
Yeah. So it's deformed away from the CFT, and we are doing conformal perturbation theory. We are doing conformal perturbation theory. So we are calculating this in conformal perturbation theory. So that's the thing. Right. Irrelevant. Yes. It's irrelevant. Yes. So okay. So now let me. So this is the motivation, and this is the reason. And there is a proposal. So there's a proposal for even the entanglement entropy in these theories by Debord and Jetta using the Wilson line approach. Okay. So because it has to be generalized. I mean, these theories admit infinite gauge symmetries, and it cannot. I mean, the notion of a geodesic has to be stated in a gauge invariant way for these theories, and there is a generalization of that. There is a generalization of that by Debord and Jetta, and so there is in fact a formula for such things from the holography. But I think after the proposal came out, I mean, there was no checks, for instance. I mean, of course, they had self-consistency checks among those things. So what we do is we actually do a CFT calculation to check this, and that's what I will try to talk about. So before we go ahead, because this is a general audience, I thought I will review this free field or the two-interval calculation for arbitrary CFT. So this is basically done by the replica method. So I'm reviewing that. So I hope the motivation of my question is clear, and maybe even if I don't arrive at the end point, I hope you understand that this is what has been achieved. So let me sort of how is EE RE evaluated in CFT. So it's basically the replica trick, and I will actually go through the pictures which Rob Myers drew, but slightly differently. So let's consider evaluating trace of e to the power of minus beta h. Okay. So what you do is, so you have the CFT on the line, and there is a beta temperature, and you would evolve the CFT and then sew it together. So that's what you would do. So you would evolve the CFT and evaluate. So you'll evaluate the path integral on the cylinder, basically. So that's what you would do. But what you would do for the partial trace? So if you have a partial trace, say, what you would do is basically, I'm just drawing it in pictures, but I hope it is clear, is basically take this, and the sewing is the trace. I mean, attaching them and integrating over the fields here, or you can imagine spins, is basically the trace operation. So you would trace over this. Okay, this is partial trace. And this is a partial trace. And you will have fields on this. So it's a matrix. So there are fields here and there are fields here. So it's a matrix actually. So you are evaluating the path integral and you're sewing on this side. Okay. And so the trick is basically evaluate trace rho a to the n. So that means basically you'll have to attach another cylinder on this. Okay. So you can imagine this as multiplication n times. So you'll have to attach another one here, and then finally it comes back. I think there were pictures of this kind and his talk. So there should be n copies. So trace rho a to the n is the partition function of the CFT on this n-sheeted surface. So that's what I mean, partition function on the n-sheeted surface with this interval, because that is sort of marked for us because the sewing is done on the interval. Okay. So partition function on the n-sheeted surface, and of course normalized by the original 1 to the n. Okay. So, what are the sort of, just to make this a little bit explicit, because I said I will do it. So, what are the boundary conditions? So, basically you have n copies of the CFT, n copies, you have these integrals, and the copy, the identification of the fields schematically is the following: tau is equal to beta minus sigma belonging to A B. So, A B is the interval, say. Yeah, there is a boundary condition, and at that tau beta minus, so this is beta minus here, it is attached to the next copy, and so on. So, the nth copy is attached to itself. Okay. So, there is a result that this partition function is equal to, so which I will motivate again, is equal to 2-point function of twist operators. So, this was mentioned, or branch point, some people call it branch point twist operators. So, this was mentioned earlier. So, this is, so I will prove this, I mean at least indicate the proof of this later, but let us suppose we accept this for the time being and see what is sort of the result. So, the dimensions of this branch point is supposed to be a primary, this object, and the dimension, conformal dimensions of these guys, of this operator, is basically central charge by 24 n minus 1 by n. Okay. So, that is the dimension. So, let us calculate the 2-point function. So, let me just go through this recipe first. So, let us calculate this thing. So, trace of rho to the n is tau n at delta, tau bar n at 0, tau, which is some epsilon by delta to the power 4 dn, holomorphic, anti-holomorphic, and the distance delta. So, this is basically, and if you take 1 by 1 minus n log trace rho to the n is c by 6. So, substitute dn, c by 6 n minus 1 by n times 1 by n minus 1 from here times log of delta by s. So, that is c by 6. So, this is the Rene formula. Of course, n going to 1 limit, we reproduce the entanglement entropy. Okay. So, of course, here I have not told you this. I have not told you the reason for this. So, this argument is basically due to Cardi, I think, is the following argument. Okay. And of course, you can explicitly okay. So, let me just go through the following argument of Cardi first. So, what he considers is basically the insertion of a stress tensor on this multi-sheeted surface. Okay. So, he considers the insertions of the stress tensor on the multi-sheeted surface, okay. And it can be evaluated. So, this one insertion of a stress tensor on a multi-sheeted surface can be evaluated by using the uniformization map. So, let me, this will play a role in our thing again, map. What is the uniformization? So, it is basically mapping these multi-sheeted surface to one complex plane. So, y1 and y2 are the locations, say, of the endpoints. So, here is the map. So, you can see it is like an n-fold covering map, 1 by n. I mean, you can imagine the square root 2, which you sort of teach in the complex analysis course. Yeah, it is a generalization of that. And if you want to evaluate this, you can use the conformal transformation. So, if you use the conformal transformation, so again I am going through this. So, if you use the conformal transformation to the omega plane, to the uniformized plane, it is basically del w by del z the whole squared, T of w plus the Schwarzschian. Okay. And T of w, okay, on the w plane. So, this is uniformized plane, it is just a simple plane. By translation invariance, this is 0, and wz you can compute. Wz is the Schwarzschian. Okay, let me write a formula for that. It's a formula in terms of the map. It's a formula like that. And you can show that this is basically, I mean, when you do this calculation, it will and evaluate t of z to the power r to the n, you will be able to see that it's actually a 3-point function of the stress tensor with some primaries inserted at y1 and y2, and each of them have dimension dn is equal to dn bar c by 24. And so this is one method of doing it, doing this calculation actually. So so this is an argument for any general CFT that how this works out. And yeah, Schwartzian, if you compute this Schwartzian, so because this is 0, so this is Schwartzian. So you compute the Schwartzian, you can show that it is actually a 3-point function with this 3 primaries of this kind. So that's the thing. So of course, what is this twist operator right now seems quite mysterious. It just changes the boundary conditions here. But in free theories, in free CFTs and like free bosons and free fermion, there are free fermion, especially free fermion. Let me say about the twist operator a few words because that will play a role. How much time do I have? 25 minutes, okay. Okay. So the twist operator for free fermions, there are explicit constructions. There's explicit construction in terms of the bosonized fields, in terms of the corresponding bosons. But for free bosons, though there is no explicit construction, you can find all the correlators required using methods developed, I think, in old string perturbation theory days by Dixon et al. I mean, Dixon, Friedan, Martinek, Schenker. So there is that. There is a technology for free bosons and free fermion CFT to calculate these correlation functions if necessary. So now let's go back to our question. I won't go through the explicit realization, but let me tell you that there is an explicit realization. Okay. Let's go back to the question. And I said that this W symmetry or CFT is deformed by this W occurrence is what we are interested in. And of course, so for n free complex fermions and n free complex bosons, they admit W theory. So W symmetry, in fact, this is something called a W1 plus infinity algebra. And in that parameter, this is at lambda equals 0. I said there was a parameter of this. Just so that I won't tell you with all these words, let me give you the current, which is quite easy to see. So of course, you know the stress tensor for a free fermion theory would be something like sum over the various copy indices or various indices, flavor indices of the fermion. So this is sort of the stress tensor. If there, in fact, the 1 is actually the U1. So there is a U1 in this case, psi star psi. And what is the W? It has to have weight 3. So there's some normalization. So of course you can see that. So you see it's dimension 3 fellow plus star plus other sort of so things so that it makes it a primary. So there is a W like that. And similarly for the free complex boson, okay, stress tensor everybody knows it's del x bar, and a W current, there is a W current. Up to some normalization, it's del squared x, del x minus del x, del squared. So this is one is bar. So there is a realization. So if there is a realization, so there is free CFTs admit W currents, and there are these twist operators in free CFTs. So of course you can do this, the question which we addressed, we can do this calculation in the free CFTs. So let me at least say how roughly this calculation is set up. And so basically, so we have this CFT and we have these n copies. And this is a deformed CFT. mu, as I said, it's a deformed CFT. And what we need to evaluate basically is, okay, so let's see the normalization. So this is Zn to the, say, mu. This is partition function, so this is normalized. So we need to evaluate following things in the perturbation theory. So once you see the structure, you would see it. So of course, the simple twist operators, so that's the leading order, plus mu times tau n bar. So these things are at the position of the endpoints, y1, y2. The single current brought downstairs, meaning this is in the exponential, so I'm sort of bringing it down perturbatively. So I'm bringing it down perturbatively. So there's a first term, and of course there's an anti-holomorphic version of that. So with the d squared w bar, and of course there is this other piece, the mu squared piece. Yeah. D squared z. Yes, yes. Holomorphic currents, yeah.
So what is the dc bar integral doing in that one?
Yeah, so it's an integral, so d squared z is basically an integral over the cylinder or the plane, right? The full, yeah, so the beta comes. So one is the real line integral and the other one is the beta integral. So that's how, okay, when I tell you how we get the final answers, I will tell you how the integration is done,
Did you tell us what this first operator is?
Yeah, so for free fermion theories, I haven't, where there is an explicit construction, I haven't told you. But for free boson theories, there are methods to evaluate it. In fact, for free, okay, maybe people are asking, okay, maybe I should tell how in the free fermion theory it is constructed. Where go? So I didn't tell you because I thought, okay, in fact, I should mention, okay, before I go ahead, I should mention we can calculate this without a free field realization. But let me give you since people are curious, so I will tell you the free field realization. So here is it for free fermion theory. Yeah, since it's sort of a discussion thing, so let me tell you. So free fermion theory, twist operator. Okay, how do you construct it? So what you do is, so you have this n copies of free complex fermions, say, okay, and you can bosonize them, phi 1, the bosonized counterparts. Basically, bosonized means psi is e to the I phi, psi bar is e to the minus I phi, and so on. So there is a bosonized thing for this. And what you do is you construct a discrete Fourier transform of this. So these are n copies. You construct the discrete Fourier transform, psi 1 plus so yeah, so this is psi 1 tilde. Okay. Similarly, the next discrete Fourier mode, the Fourier momentum mode, is 2k by n psi 2. So that's your psi 2 tilde. So the going from one n to another n is basically it's like cyclic permutation of this guy. So that means it basically multiplies. If you see the operation, if you shift psi 1 to psi 2, it basically multiplies this by a phase. It multiplies this Fourier mode by a phase. And those, so it's like in string theory parlance, it's basically a Zn orbifold. Okay. And for that, the twist operators are the following. So you look at bosonized counterparts of this, phi 1 tilde, phi 2 tilde, and so on, and you construct the following. So here's the twist operator. Product j is equal to minus n minus 1 by 2 to j is equal to n plus 1 by 2. So this is the right one which implements the twist boundary conditions. So I j phi tilde j, because this is the Fourier copy, by n. You look at the Fourier copy, bosonize each of them, and consider exponential operators with various the Fourier labels j by n. And if you actually, and this is running from here to here, and if you just evaluate the conformal dimension, it's basically the sum of half j squared by n squared, running from n minus 1 by 2 to n plus 1 by 2 in steps of integers, and that will be the dn formula for c equals 1 if you do. So this is the explicit construction of the twist operator. So it's only in free fermion theory there is an explicit construction of the twist operator, but in the free boson theory you can calculate what you want. I mean, there are rules for doing that. You can calculate it actually without an explicit realization like this. So I hope it's a bit technical to construct this thing. So let's go back. Yeah, 3-point function vanishes. 3-point function. So I will. So 3-point function vanishes. I will tell you. So and then there is a 4-point function, which is w. So there are two integrals. There is z1, there is z2 with the insertion of wz1, wz2, and so we are talking about the 3. So till of course higher orders we examine this order. So but this order we can show that it is 0. But so there is an easier way. Of course, you can explicitly calculate it, but the easier way to show it is 0 is that I mentioned that about this uniformization map. So you wanted to evaluate the 1-point function of the stress tensor in the presence of the twists or in the Rn copy. So that means in the presence of the twist. So you map it to the W plane and calculate there. So if you do that, it's basically and W is a conformal primary. So it's basically, and it doesn't have any Shorttian or anything. It doesn't have an anomalous transformation property. So it's basically some delta. So let me write this. Tau n bar W is equal to W to the Rn, which is del W by del Z. Of course, we have explicitly calculated it. The Z in the so this is in the W plane. And it's 0 by translation invariance. So this is 0 actually. This thing is 0. Now how do we calculate this? So how much time do you have? 10 minutes. Okay. So let me. So how to calculate this? So basically we have tau n, the twist operator y1, tau n bar y2. So these are the 3 0 primaries. So we have to calculate this, and by conformal invariance. So I will present one method, and we have done checks on that. Okay. So I will present the first, and I will indicate the checks. I will tell you the checks. So by conformal symmetry, it's of this form. Dn. And Dn was the dimension of the twist operator. So this is the conformal symmetry, and x is the cross ratio. What's the x? And delta, what is delta? Delta is this positions of the insertions of the twist operators. Okay. And what is x? X is the cross ratio. So this is the cross ratio. So x is the cross ratio. And note that this, in this case, you can actually show, because these are holomorphic currents, this cross ratio is holomorphic. There's no x bar. So these are holomorphic currents, so the cross ratio is holomorphic. So that's important. And then let us look at all the symmetries and try to fix f of x. So that's what I will try to do. So first, f of x is a holomorphic function in x. Okay. There is z1 going to z2 symmetry, is a symmetry of the correlation function. So there is a, if you translate that in the cross ratio, it becomes f of x is equal to f of 1 by x. And you can check if you interchange Z1 and Z2, yeah, I guess that's what it becomes. Yeah, I suppose, yeah. So that is what it becomes. And then look at Z1 going to Y1 limit, or Z2 going to Y2 limit, or corresponding Z2 going to Y2 limit and Z2 going to Y1 limit. So here x is going to infinity. You can track it. So this is basically in the cross ratio language, x is going to infinity and x is going to 0. Okay. So x is going to 0. So that means it's like Z1 going to Y2. So we need sort of information about the OP of W tau. So we need that information. So right now we don't have anything about tau, but we can sort of get an information of W tau. So how? So W Z tau n y. So this is a twist operator. So and this is just a holomorphic current. It's in the untwisted theory. So this is an untwisted operator. It's an untwisted sector. This is a twist. So we'll have a twisted sector here. So it's some O. So let's say the leading term is some operator times n. And this twist operator is actually the ground state. I mean, by construction, actually, it's the ground state of the twisted sector. So this is the ground state twist operator. And you would imagine, okay, so it's a twisted sector. So let's put tau n. Let's put if this is what is the first state in the twisted sector. So you can put tau n itself or tau n bar itself. But that structure constant is 0 because Wz tau n y tau n bar y is 0. That's what we have already seen. So that is 0. Now let us look at the dimensions. Okay. So in dimensions, so it is 3 plus dimension of the tau n, which we know, okay, equals m plus dimension of O. Okay. M plus dimension of O. So m is the confined. So it's m plus dimension O. Now we know that m has to be less than dimension of O has to be m is less than 3. The reason is that, okay, so the dimension of O has to be bigger than the twist operator. So this has to be bigger, the dimension, because as the ground state is the twist operator. So the dimension of this guy has to be bigger than the twist operator. If this is bigger than this, m has to be less than 3. M has to be less than 3. Okay. I hope that balance is clear. So if m is less than 3, the next thing is m is an integer. I mean, it's a positive m and it's less than 3. So m is less than 3. So how can it be? M is less than 3. I mean, m is an integer. So W, so this is a subtle part of the argument. W is actually, you remember the W was W current in all the copies, okay, all the copies of this Riemann surface. So and Wi, so it's an invariant object. Okay, it's an invariant object. So it's a sum over copies. Wi tau n shouldn't change it because this basically permutes the copies. The twist operator, as I saw, it changes the boundary condition. It permutes the copy. So this should be invariant, meaning the sum over I will be sum over I. Therefore, okay, I will give, though it might seem not very, I mean, some people might not believe it, but I will give other arguments, other methods of checking. So this should be invariant. Therefore, there should not be any branch points. In the OP. There is no change of the boundary conditions of the sum over OI. So therefore, there should not be branch points. Therefore, m has to be an integer, and that restricts m to be an integer less than 2. And here is the possible option. So let me write it out. What is the following? What's the form for f? So f of x is equal to a to 1 by x squared. So it has to have that x going to 1 by x symmetry. So, this is the possible option, and you can rewrite it by another cross ratio by introducing this, and so it is basically something like 1 plus f1 eta plus f2 eta squared. And this is just rewriting this thing by another cross ratio eta. Eta is something nicer. Eta is so there is another formula for this. So, basically you are boiled down to fixing 3 numbers f1, f2, okay. And you can fix f1, f2 by looking at actually the WWOPE. So, you look at WW, so there are 2 W's there, and you look at WWOPE for a general theory which admits a W current, it is known, okay. And basically WWOPE is the sum of these 1-point functions, okay. And you can plug it inside there, inside this, and try to fix this f1 and f2. And indeed, of course, that will involve evaluating then 1-point functions of tau of the stress tensor with the twist operators, and for which you use the uniformization map. And we have done it, and it looks like there are more parameters because there are so many terms in the WWOPE, but we have only 2 parameters here. It seems to be over constrained, but I think there is a solution which uniquely fixes this. And let me just give you the answers for f1 and f2. I mean, just to say that we have done all this. N to the power 4. So, there is an answer for that. We have done this, and let me indicate the cross checks for this correlator before we go ahead. I wrote down the cross checks before we sort of go ahead and just conclude. Okay, I haven't. So, one of the cross checks we have done is that this method can be done to calculate also tau n y1, tau n y2, and 2 stress tensors insertions. You can apply the method we developed with 2 instead of this holomorphic currents, but the stress tensor holomorphic current. You can do that, but this is related to 1-point function by conformal Ward identities. Okay, so 4-point function of stress tensors with 1 insertion, you can relate it using conformal Ward identities to 3-point functions. And if you calculate the 4-point function that way and the method I outlined, it works out. Then there is another method, we have cross-checked our answer. Of course, for free field, this works out because we have explicitly checked with free field also. That was our first calculation. There is another method. That method is basically, again, uniformization, but it involves 2-point functions. So, basically in the uniformization, there are various cones. And we have basically sum over Wi, and this every strip, every Riemann surface gets mapped to a Riemann sheet gets mapped to a cone, and there are various Wi's inserted, and we have to evaluate the 2-point functions of these Wi's, which is of course fixed, but you have to sum over images in this method, and doing that also gives this answer which I have indicated. So, now that we have the answer for the correlator, the next step is to make it into a cylinder, to do the conformal transformation on a cylinder, which we can do. Okay. So, let me just sort of tell you, outline how that happens. So, once you have the correlator, so trace rho to the n by 1 minus n is the leading term, log sine hyperbolic pi by beta delta plus some S2 correction n. So, S2 n is basically with all the normalizations and so on, mu squared n minus 1, 2 integrals over the cylinder. So, f1, these are those numbers, f1 eta to the power beta plus f2 eta to the power beta squared divided by sine hyperbolic. Okay. So, these are some things which come out of the and this eta is basically the same eta written in cylinder coordinates. Okay. So, you can make this will become sine hyperbolic and so on. So, there is an sort of answer in the cylinder, and then you have to perform this integral. And if you perform this integral, so let me first state the answer. You will get 2 terms. so it's far away, but there are these two terms which appear after you perform the integrals. So it's, as I said, the mu squared correction is mu squared by beta squared. Let me, so that I don't have to refer to that. So the correction is mu squared by beta squared plus some function of delta and beta times some function of delta and beta, and this has like f1 times I1 plus f2 times I2. This is the answer, and I1 and I2 are these answers. And of course, you can check many things. I mean, if you, as I said in the first thing, if you take the size to infinity, it should reduce to the thermal entropy correction, which has been evaluated by Matthias and collaborators, and that it does. Then, of course, the most non-trivial check was that I mean, there was a proposal. This was one of the motivations. There was a proposal in holography. So I'll just outline that and then end. I think I have enough time for that. Yeah, time is over. Sorry. Yeah. So there is a proposal in holography, which of course I didn't. That itself takes some time to explain. But and I didn't explain the prescription. I can explain the prescription to do the integrals to people who want to know. But there is a very precise method of doing these integrals and getting this answer. And there's a prescription in holography. Basically, it works in the Chern-Simons language. So this is ADS3, and for the higher spin, people actually, the persons involved in the proposal basically considered SL3. So there is a spin 3 bulk dual, and they looked at the following Wilson line. So this is a proposal. It's basically first what they do is they cast the geodesic in terms of the Wilson line in terms of the SL2. For the SL2 thing, and then they generalize it, and they have to somehow take the adjoint representation, path ordered. So these are the 2 points, P and Q. P, A minus, and another path ordered. So these are the 2 left and right connections of the black hole solutions. So this is dual to some black hole in the boundary, in the bulk, and they have to evaluate the following connections, the left and the right. And if you evaluate this, if you just take the flat connections for the solutions, because all the solutions are flat, plug it inside, evaluate it, there is a closed form answer to all orders in mu. And if you expand it to this order, it's precisely this thing for an SL3. And this was in general considerations, and so of course it agrees with this proposal. I should say that the lambda parameter is actually in this part of the OPE, which is actually primary, and if you take 1-point functions, it disappears. That's how the universality appears. And yeah, so this is so I should mention. I mean, we have done this on the torus for free fermions, and yeah, that should come out. I didn't have chance to discuss those results, but it should come out maybe in a couple of days. Yes, that's all.